It orbits Saturn in near silence, bathed in gold light and shadow. From a distance, it looks unremarkable, a cold, hazy world, smaller than Earth's moon, with no glint of oceans, no flash of storm. But Titan is not like other moons. It is a world of contradictions, a place where rivers run, but not with water, where rain falls, but not from clouds we know, where dunes stretch for hundreds of miles, tall, dark, and alien. Titan is Earth's strange twin, shaped by chemistry, sculpted by wind, and wrapped in an atmosphere thicker than our own. And among its most intriguing features are the dunes. Massive, sweeping ridges of material stretching across its equator, winding like black ribbons across a frozen desert. We've seen dunes before, on Earth, on Mars, but these are different. These are dunes formed in a world without sunlight, without sand, without anything we fully understand. They are one of Titan's great mysteries, and they might hold the secrets to its past and perhaps its future. When you look at Titan, you don't see a surface. You see atmosphere, thick, opaque, orange. Titan is the only moon in our solar system with a substantial atmosphere. In fact, it's denser than Earth's. At ground level, you'd feel the weight of its nitrogen-rich air pressing down, gentle but present. The skies are filled with complex hydrocarbons, molecules that fall from the upper layers like chemical snow. Sunlight, filtered and broken by this haze, barely reaches the ground. Temperatures hover around -290 degrees Fahrenheit. Methane and ethane are not gases here. They are liquids. They rain. They flow. They pool in lakes and carve channels through icy terrain. This is no barren rock. It is an active world. And it is here, on this alien surface, that the dunes form, not from sand, not from stone, but from something darker and stranger. At first glance, Titan's dunes resemble those of Earth's deserts, long, linear ridges shaped by wind, consistent in height and spacing. But what forms them is a mystery. They are made not of quartz or silica, but of a material we've never seen in dunes before. Scientists believe it's organic, tiny particles of frozen hydrocarbons, possibly born in the upper atmosphere, where solar radiation drives complex chemistry. These particles fall from the sky like soot, settle on the surface, and are carried by Titan's winds. Over time, they accumulate. They align. They form ridges as tall as skyscrapers and as long as cities. Some scientists call this material tholin, a tar-like substance rich in carbon and hydrogen, unlike anything we know on Earth. It is soft, sticky, strange, and it may be the key to understanding how prebiotic chemistry could arise in places far beyond Earth. The dunes tell us something fundamental. Titan has wind. And not just wind, but regular patterns, seasonal currents capable of shaping the surface over centuries. This is surprising. Titan's dense atmosphere and low gravity create unique conditions. Winds move slowly, but carry great power. When they come, they can lift fine particles and push them across great distances. And they do so under a sky lit not by day and night, but by long, gradual seasons. The dunes are aligned east to west, suggesting a global wind system driven by Titan's orbit around Saturn. But new models have complicated this view. Some data from NASA's Cassini mission hints at shifting winds, storms that reverse direction, gusts that come only during equinoxes, transient but powerful enough to reshape the terrain. This is not a dead world. It is dynamic. It moves, breathes, erodes. And the dunes are its signatures, records of wind and time etched into the surface. We owe much of what we know about Titan's dunes to the Cassini spacecraft, which orbited Saturn from 2004 to 2017. Cassini's radar penetrated Titan's haze and revealed a surface covered in strange terrain, lakes, mountains, cryovolcanoes, and dunes. Vast fields of them, stretching across the equatorial regions. These dune fields are enormous. Individual dunes can be hundreds of feet tall, stretching for miles. They form in parallel bands that snake across plains and around obstacles. They respond to wind, topography, and time. Cassini gave us maps, not just of where the dunes are, but how they interact with the landscape. Some wrap around mountains. Others are deflected by ancient impact basins. Still others appear to bury older terrain, suggesting they're active, growing, alive in geological time. Cassini didn't just show us where the dunes are. It showed us that they're still forming. To understand Titan's dunes, we must understand Titan's climate. Unlike Earth, which has a rapid daily cycle and relatively quick seasons, Titan's seasons unfold over years. One Titan year is nearly 30 Earth years long. Its equator experiences long periods of dry calm, followed by brief but intense methane rains. The dunes exist mostly in the dry zones, but scientists believe that changes in Titan's orbit and axial tilt, similar to Earth's Milankovitch cycles, may drive long-term climate shifts. These shifts could alter the winds, redirect the dunes, bury or expose ancient layers. In the patterns of the dunes, some researchers see a climate record, a fossilized history of atmospheric change going back tens of thousands of years. It is a kind of geological memory, a record not in rock, but in sand-like carbon. Reading those patterns could tell us how Titan has changed and what may come next. Titan is cold, harsh, chemically exotic, but in many ways, it is the most Earth-like world we know beyond Earth itself. It has rivers, lakes, rain, erosion, dunes, weather, and complex organic chemistry. Some scientists believe Titan is a prebiotic world, a laboratory of early Earth conditions. In its atmosphere, energy from sunlight and cosmic rays drives reactions that form molecules essential to life. On its surface, those molecules accumulate, concentrate, interact. Could life exist here? Not as we know it, but as a slow, cold chemistry adapted to methane and ethane instead of water? Some think it's possible, and if so, the dunes may play a role. They could be reservoirs of organic material, gathering places for the building blocks of life. We don't know yet, but the mystery deepens the more we look. In the coming years, Titan will receive a visitor. NASA's Dragonfly mission, a rotorcraft the size of a car, is scheduled to launch in the 2030s and arrive at Titan years later. It will fly through the haze, land on the dunes, sample the surface, analyze the chemistry. It will go where Cassini never could, down to the ground. Dragonfly will explore dune fields and impact craters. It will taste the carbon-rich soil, search for complex molecules, and send back data no probe has ever collected. And as it does, it may finally tell us what the dunes are really made of, how they form, how they move, and whether, beneath their soft, dark ridges, something ancient or alien waits to be found. On Earth, dunes whisper of wind, of motion, of time. They shift with the breeze. They march across deserts. They record the weather of the world. On Titan, they do the same, but in a tongue we are just beginning to translate. They are silent rivers of dust and carbon, shaped by alien winds, sculpted over centuries, touched by rains of methane and the slow gravity of a distant moon. They tell a story, not just of erosion and climate, but of chemistry, of potential, of mystery. In their long, black shadows lie clues to Titan's past, and perhaps to life's future. And as our machines prepare to land, to measure, to listen, the dunes remain.